the conversion from analog to digital values. The ATmega 328P has a dedicated hardware integrated whose task is to do exactly that. What is the content of this chapter in particular? First of all, we live in an analog world and hardly we experience digital or discrete values. To use the analog values in a digital domain, they need to be converted. And that is the purpose of the analog to digital converter, or ADC. In this chapter, we will discuss some fundamentals of the ADC and later on how to use the ADC in the ATmega. By the way, also the counterpart of the ADC exists, and it is called digital to analog converter, or DAC, an essential part used for instance in audio devices or also in ADCs. Let's have a look at the voltages that count as 0 and the ones that count as logic 1. This is from the datasheet of the ATmega. A logic 0 here, VIL, is the input low voltage and it depends on the input voltage VCC. If the ATmega is supplied with a voltage between 1.8 and 2.4 volt, logic 0 ranges from minus 0.5 volt to 0.2 into VCC. Hence, at 2.4 volt, the highest voltage that is still ensured to be read as 0 will be around 0.5 volt. It is a bit more for higher VCC. For the Arduino supplied with 5 volt through the USB port, it will be 1.5 volt that is still read as logic 0. For the logic 1, the voltage at the input pin has to be between 0.6 into VCC and VCC plus 0.5 volt. So for the Arduino again, the voltage has to be between 3 and 5.5 volt. As you can see, an analog voltage range is defined to express two distinct digital values. But what happens in the gap between logic 0, whose highest voltage level is 1.5 volt, and logic 1, whose lowest voltage level starts at 3 volt? What if we need more distinctive values and not only 0 and 1? For instance, if we measure the air temperature, we could decide between hot and cold, or freezing point or not. However, we might want to know if it is, for instance, 0, 20 or 35 degrees Celsius outside, since that depends on how many layers are we going to wear. And those are already 3 distinct values. Therefore, we need more distinct values. And the more we have, the more accurate we can express the analog value. For instance, instead of 0 and 1, let's divide the range from 0 to 5 volt into 1024 distinct values. 0 represents 0 volt, and the highest, that is 1023, since we start counting from 0, represents 5 volt. That allows me to use any integer between 0 and 1023, for instance 511, which is a bit less than half, a quarter, an eighth, or an arbitrary value of, for instance, 572. The integers turn out to be representations of voltages, and as you can see, there is no large gap between logic 0 and logic 1, since the integer values are evenly distributed between 0 and 1023. Translated into voltages, now the steps between two consecutive increments is 5 volt divided by 1024 steps, which is equal to 4.88 millivolt. If we had 2048 distinct values, the increment would have been half, that is 2.44 millivolt. The more distinct values I have, the more accurate I can approximate the analog value. If I had infinite distinct values, then I am in the analog world. Unfortunately, there is no infinite accuracy in the digital domain. So currently we have to be happy with 1024 values, which can be represented using 10 bits and a maximum error of around 4.88 millivolt. Let's consider an example. A voltage of exactly 2.8 volt is presented. As you can see, it is neither in the range of logic 0 nor in the range of logic 1. So we do not know how a digital input pin will sample that value. It might be 0, but most likely it will be 1. It depends on the chip, the manufacturing process, and will be different from chip to chip. Since the Arduino is powered through USB, VCC is 5 volt. R represents the value, that is the integer, and V is the resulting voltage. Now we start sampling the 2.8 volt, and I would like to come as close as possible to the 10-bit digital representation of the 2.8 volt. First, we consider the most significant bit. The integer 0 represents 0 volt. Since 2.8 volt is a lot higher than 0 volt, we set this most significant bit to 1 and have a look again. Now, the integer 512 represents almost exactly half between 0 and 5 volt. It is 2.5024 volt, which is still lesser than 2.8 volt. Let's have a look at the other bits. The second bit from left, if this one is set to 1, then the result is 768, which is 3.7537 volt. However, that is too high. Whenever we set a bit, we increase the integer, and with that, the resulting voltage value. Therefore, we would not be able to come back to a lower voltage of 2.8 volt if we kept that second MSB set. Therefore, it is better to keep it cleared and try the third MSB. If that third MSB is set, the value is still too high, so this bit is not set either. Still too high, but we are getting closer. Okay, that is too low. Therefore, we keep the current bit. We are only halfway done. Let's continue with the next bit. And this one. We are getting closer and closer to 2.8 volt. In fact, here we are already below the error margin. Unfortunately, the annealing algorithm is quite stoic and does not know anything about error margins. It is basically following the rule: if the nth bit is considered and the resulting voltage is too high, clear the bit and move on to the next bit. The resulting voltage is currently 2.8006 volt, which is just a little bit higher than 2.8 volt. We know that the maximum error is 4.88 millivolt. Since the difference between 2.8 and 2.8006 volt is only 0.6 millivolt, we are well within the error margin. Unfortunately, the algorithm continues to follow the rule and clears the bit. Since there is no other bit left, the algorithm exits. As you can see, due to the last change, the error increased to 4.4 mV, though it is still within the margin. To prevent this from happening, we have to adapt the algorithm and make it more complex. Higher complexity means lower clock rates. Probably it would be easier to add another bit for accuracy. However, then the question is, when will we stop, since we just keep postponing the problem? No matter the complexity of the annealing algorithm, how do I get the value of 572? And for that, the ATmega is equipped with an analog to digital converter, which does exactly what we just did, but automatically and a lot faster. Let's talk about how the ATmega converts an analog value into its digital representation so that you, as a developer, can make the right choices and use it in your program. In the world of Arduino, it is simply a function call to analog read. However, it is a bit more complicated than that. The ADC can be tuned not only to increase the accuracy, but also its sampling speed, as we have seen in the previous chapters, in which the ADC was able to sample so fast that we had to set the UART transfer rate to 1 million bits per second to get the values out of the ATmega. That speed cannot be achieved using the Arduino library call. But first, let's zoom a bit into this circuit diagram and have a look at the pins represented by those little boxes, as always, on the left. Here we have pins called ADC0 to ADC7, ground, AREF and AVCC. These multiplexers allow the developer to choose which pin value should be forwarded. It's an exclusive choice. Apart from the pins, the developer can also choose from internally connected options, such as an internal 1.1 volt reference, the bandgap reference, and interestingly, a temperature sensor. Let's talk about those choices one by one. First, the pins, ADC0 to ADC7. Where are they? Here is the pinout once again. ADC-related pins are marked in yellow. As you can see, port C is used to establish connectivity from the outside world to the ADC. Then we have the reference voltage, AREF, and AVCC here. So far, I have not mentioned these two pins, which are also in yellow and therefore related to the ADC. Those pins will be handled in the chapter about the analog comparator, which is also a periphery of the ATmega. More about that later. As you can see, port C has only 6 pins. However, earlier I mentioned ADC6 and ADC7. Where are the other 2 pins? If you need all 8 connectors, also called channels, to the ADC, then we cannot use the 28 DIP that the ATmega is usually packaged in for the Arduino. Other packagings expose pins ADC6 and ADC7, here and here, and here and here, along with the original ADC0 to ADC5. Let's examine the upper 3 pins first. AVCC, the internal 1.1 volt reference, and AREF. Based on a setting of this multiplexer, either of them will be forwarded to the 10-bit digital to analog converter. This so-called reference voltage represents the maximum voltage the input voltage that is to be measured can be compared against. What is the impact of this reference voltage, and why would anybody want to change it? As already mentioned, the reference voltage is the maximum voltage that can be measured. Any value above this reference voltage saturates the ADC, which means it always returns the maximum possible integer value of 1023. Let's say AVCC is 5 volt, which is the case in Arduino. That means the maximum voltage that can be measured is 5 volt as well. Therefore, between 0 and 5 volt are 1024 distinct increments of 4.88 millivolt. If 1 volt is given to the ADC, it will return its integer representation. In this case, despite the correct value would be 204.6, it needs to be rounded up to 205, introducing an error of approximately 2 millivolt. Please note that AVCC should always be connected to VCC, even if the ADC is not used in a project. Its maximum variation can only be VCC plus minus 0.3 volt, and it is advisable to filter the power supply voltage through a low-pass filter. Back to the example. Many times, the maximum voltage is a lot lower. Imagine a 3.3 volt sensor. Its range is between 0 and 3.3 volt, or even a sensor that returns a value between 0 and 1 volt only. Since in that case 1 volt is the maximum, it would be nice to reduce the reference voltage and hence increase the accuracy. Instead of increments of 4.88 millivolt, a reduction to a reference voltage to 1.1 volt means that the increments decrease to a little over 1 millivolt, 4 times the accuracy for the same amount of bits in the integer, that is 10 bit. And we get this accuracy for free. And that is why the AREF pin is exposed. It does not have the limitations of AVCC and does not need to be in the range of VCC. AREF can be selected freely between 1 volt and AVCC. In this case, in which the sensor returns an analog value between 0 and 1 volt, we do not have to use AREF at all. For convenience, a voltage of 1.1 volt is generated internally, and we configure the ADC to use that one instead. We will come back to this a little bit later, and we will see what else we can do with it. For now, let's talk about the other pins. In the previous session, we talked about these pins regarding their reference voltage. Now, let's discuss about the input voltage that is to be measured. This input multiplexer here allows the developer to select any of those sources. It can be a pin such as ADC 0 to ADC 7. It can be ground, the bandgap reference, or interestingly, a temperature sensor. Let's have a look at this discovery first. Many projects measure the ambient temperature. Usually, developers integrate external and dedicated sensors such as the DHT11 or DHT22 to accomplish this task. Those sensors are factory calibrated and therefore pretty easy to integrate. On the downside, they cost money, space and power, which might be problematic in case the system runs on batteries and the primary goal is to extend the life of that battery. Alternatively, temperature sensors are also integrated in real-time clocks to calibrate their oscillators, whose frequency depends on the physical environment, including the temperature. Often, this sensor can be read out and used instead of an extra one. One example is the DS3231, whose datasheet is attached to this lecture. The DS3231 temperature sensor is quite accurate with an error of ±3 degrees Celsius and is also factory calibrated. On the other side, the temperature sensor of the ATmega is already integrated and pretty easy to access. However, the downside is that it is not factory calibrated. That means, while external sensors reveal a maximum error in the datasheet of, for instance, 1 degree Celsius difference between the measured or reported and actual temperature, such a number does not exist for the temperature sensor integrated in the ATmega. Even worse, even if this temperature sensor is calibrated manually, this calibration is valid only for this particular chip and will be different even among other chips of the same model. Besides the datasheet for the DS3231, also attached is the avr-122, which talks about the ATmega temperature sensor in greater detail, in case you are interested in more information about it. The topic of this session is about if you do not need an ADSC and do not have the budget for an external temperature sensor, what is the issue with the ATmega temperature sensor and how to increase its accuracy. Let's have a look at an example illustrating the problem. This diagram shows the actual temperature on the x-axis, while the temperature measured by the ADC temperature sensor is on the y-axis. The red line marks the ideal case in which the measured temperature is not only the actual temperature, but it is also an analog value. In reality, it should show discrete values of temperatures that can actually be measured, like a line of dots along the red line. But assume we could measure with infinite resolution. It makes life easier for the time being. Unfortunately, the temperature sensor of the ADC does not return the actual temperature, but something represented by the green line. So for instance, if the ambient temperature is 0 degrees, the ADC sensor returns 20 degrees instead, right here. Quite a large error. At about 45 degrees, the measured temperature is quite accurate. But that is all about it. In average, it could be said that the error is maybe ±20 degrees Celsius, which renders the sensor useless for many projects. What can we do about the accuracy? And are there ways to improve it at least a little bit? And there are. Imagine the ambience temperature is measured with a calibrated sensor. The ATmega is placed into that environment and the reading settles. Let's assume the ambient temperature is 25 degrees Celsius. Now the value that is measured by the ADC is checked. it reports a temperature of 34 degrees Celsius. Then the ambience is heated up in, for instance, a household oven to 61 degrees Celsius. As a side note, if you do that experiment at home, please do not use a microwave oven, since that will destroy the chip. At 61 degrees Celsius, the reported temperature is only 52.5 degrees Celsius. We draw an intersecting line through both points, assuming with a linear increase in temperature, the measured temperature is also linear. As a first improvement, we would like to make sure that the interpolation, that is the blue line, originates at the 0 degree point. Plugging in the measured and the actual temperatures into the formula returns the T-off value. That is the value by how much we are off at 0 degrees, which is 21.15 degrees Celsius. With that information, we subtract all return temperature values by 21.15 degrees Celsius, which essentially means that we shift the blue line by 21.15 degrees Celsius towards the x-axis. But oh no, we made the error even worse. Hence, a second step. Apart from shifting the blue line around, we can also rotate it. And that is what we do in the second step. We want to rotate the blue line in such a way that it matches the red line. This is called the gain factor, K, with the actual temperature divided by the measured temperature minus T-off. Again, plugging in the values into the formula gives us a gain factor of 1.946, and we increase the steepness of the blue line by that amount. Now, the blue line is exactly above the red line. It does not mean that the error of the ADC temperature sensor is 0 by now, but it is much better compared to before. Using T-off and the gain factor, the actual temperature is the measured temperature minus the offset into the gain factor. And as you can see, while we still have errors around, for instance, here or here, the error is pretty small at exactly these 2 points. How close and for how long the error is tolerable, we might not know, as in real, we just know those 2 measuring points. Everything else in between is just blind flying and an assumption. What if we have only one calibrated measurement available and there is no option for a second measurement? Let's have a look at that situation as well. Let's say you measured 34 degrees in a 25 degrees Celsius environment. How will you rotate the blue line intersecting with the actual and measured temperature point? Since there is no way how the green line continues, as we do not have a second point, quite a guessing task. Can we make an educated guess to reduce the error and not to increase it? Sure, we can assume that the gain factor is 1 and hence the blue intersection is in parallel with the ground truth in red. If we assume that K is equal to 1, we can calculate T-off and move the blue line to be the same as the red line. Instead of 21.15 degrees Celsius, like in the previous example in which we had 2 points, T off equals 9 degrees Celsius in the 1-point calibration example. Therefore, we subtract 9 degrees from all measured values in the hope that we get closer to the red line. As you can see, while the error decreases for the measured point, unfortunately for higher temperature, the error increases by 9 degrees from the ideal ground truth. Again, we just see this increase because of the graph shown here. In reality, we would not know at all, as we just know about this point. It could also be that the error decreases at higher temperatures as well, since this is just an example. Apart from shifting the graph, what else can we do? We could assume that the intersecting blue line originates at the 0 degrees Celsius point. That means that the offset T off is fixed to 0, while we can compute the gain factor K to rotate the blue line. Let's do that. K equals the actual temperature divided by the measured temperature. We have to reduce the steepness of the blue line to match it with the red line by 0.7353. Let's have a look at the effect of that rotation. As you can see, the error is again reduced around the measured point. However, the further we are from that point, the lesser we can say about the error, and it even increases again, like in the previous example. So which one shall we choose? Shall we rotate the graph by modifying the gain factor, or shall we keep the gain factor fixed to 1 and shift the graph by an offset? In this particular example, it is quite easy to see. While the 2-point calibration is reducing the error tremendously, as shown by the dotted line, the error for the single-point calibration is quite large. In this example, it would be better to modify the offset and keep the gain factor constant, shown by this blue line. Rotating the graph results in a larger error. However, in real life, we would not know that, and it is more a question of preference if we have only one measuring point. In one ATmega, you might have a larger error if you keep the offset flexible. With another ATmega, you might have more luck. An important takeaway from these examples is that whatever the method for the 1-point calibration, the temperature measurement around the calibration point becomes very accurate. If you have a project in which the ATmega is deployed in an environment which needs to be around 25 degrees to stay with this example, then you do not need to have to go through the additional work of finding another calibration point. However, if a range of temperatures is to be measured, 2 or even more points for polynomial interpolation are required. The more calibration points you have, the more accurate you can adjust the green dotted line to the red ground truth. Okay, let's say you finished the computation for the calibration. What do you do with T off and the gain factor? Obviously, it is possible to store T off and K as constants in your program. However, then it would be necessary to recompile your program for every chip, since both values could differ drastically from chip to chip. A more convenient method would be to upload your program and execute it in a calibrated environment of, for instance, 25 degrees Celsius. When the program is started, the very first time, both T-off and K values are computed and stored in non-volatile memory. Fortunately, the ATmega is equipped with an EEPROM. Any subsequent start of the program would check if the calibration has already been completed earlier, and if so, read the values from the EEPROM. In a chapter later in the course, we will discuss the EEPROM in more details. By now, we know that the one-point calibration is the easiest. In general, it is said that in the range of 20 degrees around the measured point, the error is within 1 degree. It is not guaranteed though, and the closer you measure towards the calibration point, the higher is the accuracy. How to choose if you modify T-off and keep K constant, or vice versa? There is no straight answer. It might be okay to do it for your ATmega 328P, but not for another ATmega 328P. It's all about personal preference. Higher accuracy can be achieved with more calibration points. Imagine you have infinite measurements. Therefore, you are aware how the green snaky line looks like in the entire operational range of the ATmega. But usually, there are only a few points available, so any other point needs to be guessed. On the upside, once the hurdle of calibration has been taken, the developer is rewarded with a low cost and low power, since it is already present, temperature measuring device. Before you start working with that temperature sensor, please do not forget that for the temperature measurement, the 1.1 internal reference voltage has to be selected. To increase the accuracy even further, the ATmega 328P can activate an ADC low noise mode, in which most peripheral devices, such as the CPU and communications, are deactivated to decrease the noise generated by those peripheries. We will talk about those low noise modes in the chapter about how to reduce the power consumption of the ATmega later in this course. Or alternatively, you can go there right away and have a peek at those topics. Another option is to reduce the clock frequency of the CPU. The ATmega supports a clock frequency of up to 20 MHz, but that does not mean that you have to run it at 20 MHz. For instance, in the Arduino setting, the clock is only 16 MHz, 20% below maximum. Further, the ATmega has an internal clock that reduces the frequency to 128 kHz. Again, we will talk about that when we talk about methods to reduce the power consumption. For now, let's proceed with the ADC and see what else we have. The Bandgap Reference. Using a practical and actually important example, especially for developers deploying battery-powered ATmegas in the field, we will see what it can be used for. The Bandgap Reference needs to be selected through the input mux. For our purpose, we also select AVCC as reference voltage. What is the Bandgap Reference? The bandgap reference is a voltage that is internally generated. The ideal bandgap reference is independent of the input voltage, manufacturing process, temperature, etc. However, in reality, this is not the case. A peek into the datasheet reveals that despite multiple possible external influences, it is a surprising stable voltage. It varies by around 10 millivolts depending on the temperature. Also, the input voltage, that is VCC, has some influence. The bandgap reference drops a bit for VCCs higher than 5 volt, but till 5 volt it is rather constant. If you are aware in what temperature environment the ATmega is deployed, you can easily predict the bandgap reference for increased accuracy. As an example, let's say the ATmega runs at 25 degrees Celsius and we fix the bandgap reference to 1.1365 volt. What can we do with that now? As you know from the previous examples at the beginning of the chapter about ADCs, the ADC returns an integer, which, together with the input voltage VCC, can be used to calculate the analog voltage at the pin of the ADC. To do so, the formula is the input voltage divided by 1023 into the integer from the ADC. That results in the analog voltage. But a few slides have passed between now and then. And now we know that not VCC goes into the ADC, but AVCC. So let me replace that. Remember that AVCC is related to VCC, since it has to be in a range of plus minus 0.3 volt around VCC. Assume you configured the ADC to take the bandgap reference as an input to the ADC. However, as we have seen, the bandgap voltage is quite constant, so we know its value. Multiple times, we also read the measurements from the ADC. They are in the table at the top. So what is unknown here in this formula? Could it be AVCC? Let's see the impact of this hypothesis. I solved the formula to the unknown variable AVCC. The analog voltage is the bandgap voltage, so let's put it in. There we go. Now, if I take the readings from the ADC, I get these voltages. It turns out that I can compute AVCC if I use the bandgap reference. Therefore, and as a bonus, if let's say the ATmega is powered by a 18650 lithium-ion cell whose operational voltage range is between 4.2 and 2.8 volt, this measurement tells me how much juice is left in the battery and if it should be recharged or replaced. Especially lithium cells are quite sensitive to undercharging, and hence these readings allow the developer to mitigate damaged batteries. As you can see, the higher the reading, the less juice is in the battery. I do not even have to do the calculations below in the formula. In the program, the ADC value can be read, and any value above a threshold of, let's say, 400 will trigger some event preserving battery or asking for a replacement. Or, in other words, instead of assuming that these voltages are always constant, while these voltages here are measured, the roles are reversed. To measure how much is left in a battery, this remains constant, while AVCC changes. That means, as we had it earlier, instead of moving the red line, I changed the line of max, which then has an impact on the reading of the red line. Quite useful, but what are the alternatives if the input voltage is to be measured? Another method would be a voltage divider. We have a power source right here and two resistors. With the measurement of the voltage drop between those two resistors, VCC can be computed. One big disadvantage is that this circuit needs constant power, as a small current will flow through those resistors. Therefore, a pin connected to a transistor called SW can be used to turn the circuit on and off as shown on the right. It becomes increasingly complex. Therefore, if you require an easy way to measure the input voltage, I suggest to have a look at the bandgap reference voltage. How to configure the ADC for that? Let's start with the left part, including the pins, the input multiplexer, the reference voltage selector, and how to configure all of those. The ADMUX controls not only the input multiplexer, but also the multiplexer selecting the reference voltage. For 3 inputs, 2 bits, refs 1 and refs 0 are required. If AREF is selected, the datasheet specifies that it has to be between 1 volt and AVCC, but it cannot surpass AVCC. In addition, if there is a custom reference voltage applied to the AREF pin, you must not select any of the internal voltage references. Imagine the voltage at the AREF pin is 3.3 volt, and now the 1.1 volt reference is selected. That means current will flow in here to the AREF pin, then through the transistor, through the MUX, into the reference voltage. There is no diode restricting the flow of current. Hence, if AREF is connected, make sure that this transistor is always turned off. As you can see in the diagram, if either AVCC or the internal reference voltage of 1.1 volt is selected, this reference voltage does not only go through the DAC, which is connected here, but it also comes out at the AREF pin. That does not mean that you can hook up periphery to that 1.1 volt pin, since it is not capable of delivering a lot of current. Primarily, the purpose is to give the developer the option to measure the reference voltage. However, that is only true if AREF is not connected to anything. Further, if AVCC or the internal 1.1 volt reference is selected, it is advisable to connect a 100 nanofarad capacitor to the AREF pin to reduce noise levels. With that capacitor in mind, imagine that you selected the AVCC pin at 5 volt and switch over to the 1.1 volt reference. The wire here, and especially the capacitor, will carry a charge. The question is, how fast does this line charge change to the new voltage level, since it is not connected to any ground? at least not in this diagram. So potentially it could take quite a long time. But how long? Internally, the line is connected through a large resistor of 32 kilo ohms to the ground. Hence, once the voltage changes to a lower one, the charge is adapted by being able to escape through this resistor. The RC constant determines how long it takes till around 37% of the initial charge is still left. In this case, it takes at least 3.2 milliseconds. For higher accuracy, the waiting time increases exponentially since the discharge is not a linear function. For an accuracy of 99%, 4 times of tau needs to be waited. That is more than 12 milliseconds, or in our case, since the ADC has 10 bits, it is advisable to wait for 99.9% of the charge to disappear, increasing the waiting time to 7 times tau, or around 22 milliseconds. Therefore, once the reference voltage changes, the ADC becomes unusable for quite some time, and the developer has to adjust the software accordingly. The ATmega has reference voltages of AVCC and 1.1 volt. What if you need something in between, let's say 1.8 volt? We connect a power source to the AREF pin supplying 1.8 volt. And to make this example even more complicated, as stated earlier, in case we also would like to use, let's say, AVCC, we are going to turn on this transistor at one point in time. We have to prevent the flow of current from AVCC into the 1.8 volt reference source. Therefore, we limit the flow of current by inserting a resistor called R1 between the AREF pin and the 1.8 volt source. By now, we have a classical voltage divider including R1 and the internal 32 kilo ohm resistor. Ideally, for my 1.8 reference voltage, I would like to keep R1 as small as possible. If I set it to 0, then this fraction becomes 1. And AREF equals VREF. On the other hand, I have to make sure that the current is limited. With R1 equal to 0 ohm, I am not going to achieve any limitations on the current. The question is now, what is the smallest size of R1 so that the current is not more than 1 milliampere, which is considered to be safe? How to compute this value? I will pause the lecture and show a countdown stating when the lecture continues. You can pause the lecture here to give you time to think for a bit. Continue once you have the solution. Okay, here's the solution. From high school, you will know that U is equal to R into I. And therefore, R is equal to U divided by I. Hence, resistor R1 needs to be larger or equal to AVCC minus VREF divided by 1 milliampere, which is 5 volt minus 1.8 volt into 10 to the power of 3 ampere. And that turns to be 3.2 kilo ohm. Therefore, if this resistor is more than 3.2 kilo ohm, we make sure that the current through this line is always less than 1 milliampere. But not every time the AREF equals the source VREF. What if the reference voltage is, let's say, 3.3 volt and AREF is supposed to be 1.8 volt? We use a voltage divider to get the desired voltage of 1.8 volt. Again, the question is, what values do not only R1 but also R2 need to have to limit the maximum current to lesser than 1 milliamp? Again, I will give you time to think. Well, R1 is easy to compute. We take the difference in voltages, which is 5 volt minus 3.3 volt, and divide it through the maximum current of 1 milliamp, resulting in a resistor value of at least 1.7 kilo ohms. But what about R2? Consider that R2 and the internal 32 kilo ohm resistor are in parallel. I use the same formula, but this time from AVCC to the ground, and take into consideration the current to be lower than 1 milliampere. Therefore, the parallel resistor RP needs to be larger than 5 kilo ohm. Okay, so far we know that R1 needs to be larger than 1.7 kilo ohm and RP larger than 5 kilo ohm to meet the current requirements, that in no configuration more than 1 milliamp goes through the pin. Now we have to have a look at the combination of R1 and RP to get our desired voltage of 1.8 volt at the AREF pin with a reference voltage VREF of 3.3 volt. And in the end, we will get values for R1 and R2. I'll let you do the math for the fun and continue the lecture after the break to give you tips how to get to the results. To see the relationship between R1 and RP, we use the formula for the voltage divider. We insert a ref of 1.8 volt and Vref of 3.3 volt and realize that R1 is equal to 0.8333 into RP. That is an interesting observation. If we compare the multiplicants, we have a 1 here and a 0.8333 and so on over there. That means that R1 is always smaller than RP, or in other words, RP needs to be 20% larger than R1. With that condition in mind, that the lower boundary of RP of 5 kilo ohm is larger than the one of R1, we set RP to 5 kilo ohm and check if R1 is still larger than 1.7 kilo ohm. Hence, if RP is 5 kilo ohm, then R1 is equal to 8333 into 5 kilo ohm, which is equal to 4.166 kilo ohm. Hence, this condition is met. The only value that is still missing is the resistance for R2. Using the formula for parallel resistors that we had earlier, and that was Rp is equal to R2 into 32 kilo ohm divided by R2 plus 32 kilo ohm. Inserting 5 kilo ohm for Rp gives us R2 in the end. After doing the math, we get to know that R2 is equal to 5.926 kilo ohm, or almost 6 kilo ohm. Okay, that was a session about the reference voltage, but there are still configuration bits left in the ADMUX register. In the previous session, we talked about refs 1 and refs 0, defining the source of the reference voltage. The next bit in the queue is ADLAR, which stands for ADC Left Adjust Result. The ADLAR is quite simple. It determines how the data returned by the ADC is aligned in the data register. The ADC returns an integer consisting of 10 bits, hence 2 registers with 8-bit each are required. Would you like the most significant bit of that integer to be aligned to the MSB of the higher byte in ADCH, or the least significant bit aligned to the LSB of the lower byte in ADCL? That is an interesting question, and it is not immediately obvious why this configuration even exists, since usually we would align an integer to the LSB and never set ADLAR to 1. In case you might guess that it might have something to do with big or little endian, which I heard from many of my students, this is something different entirely and has nothing to do with the arrangement here. It turns out that the ADLAR setting is quite interesting. However, I would like to defer the explanation of the setting to a session later in this chapter when we talk about the ADC sampling rate. Therefore, the last setting in the ADMUX register defines what analog input is selected. Apart from the pins ADC7 to ADC0, also the temperature sensor, the bandgap reference, and ground can be selected as well. These inputs are also called channels. As a note from experience, if you would like to read from multiple channels consecutively and change channels after one sample process is over to start the next one with a different channel, it is advisable to discard the first reading from the new channel. There might be a charge left on this wire which needs to be discharged first. Therefore, to have a more accurate reading, either wait some time or discard the first reading. That is all what I have about the ADMUX, but we have more registers. We will move on to the ADC status and control register and have a look at what we can do with that. First, the ADCSRA. In its most significant bit, it is decided if the ADC is enabled or not. It is basically the main power switch. The next bit is the ADC start conversion bit. If the ADC is enabled, setting this bit to 1 will start the sampling from the selected input. What will happen if this bit is set? Let's say the reference voltage is 5 volt and the input voltage that is to be measured is 2.8 volt. The main components of the ADC is the conversion logic, which makes the decision about how to continue, a 10-bit DAC or DAC, which is able to convert a digital input into an analog voltage, and a comparator which compares the voltage coming from the DAC with the input voltage and tells the conversion logic which one was higher. The conversion has started. By default, the conversion logic tells the DAC to output 0 volt. The comparator compares 0 with 2.8 volt and returns a 1, telling the conversion logic that the current output of the DAC is lower than 2.8 volt. The conversion logic sets the most significant bit so that the DAC generates about half the maximum reference voltage. Still, the input is higher, so the conversion logic moves on and sets the second most significant bit to 1. But with that, the DAC output is too high, hence the comparator returns a 0. This process continues till all 10 bits have been considered. The computed value is then made available in the ADC data register and aligned depending on the ADLAR setting that we had earlier. How long does it take to sample one value? Well, a single conversion takes 13 clock cycles before the result is available. As you can see here, sometime in the previous clock cycle, ADSC has been set. The next positive clock updates the MUX and REFS settings. That means that even if you change the MUX or REFS settings somewhere during the conversion, the new values only become available once the next conversion starts. The sample and hold takes 1.5 clock cycles. That means with the third clock cycle, the conversion starts, and it takes 10 cycles for all 10 bits. To make the result available in the data registers, 1 clock cycle is required, hence 13 clock cycles in total. After the conversion is complete, the ADSC bit is reset right here, and it can be set again to start the next conversion. At the same time, as soon as the result is available, the ADIF bit comes up. While a single conversion takes 13 cycles, the very first conversion after activating the ADC by setting the ADEN bit is an exception. It takes 25 clock cycles in total, mainly because the sample and hold mechanism is to be initialized. After that, every successive conversion reduces to 13 cycles. And that summarizes the effect of setting ADSC, which is also set by the Arduino function call analog read. After ADSC follows ADATE and ADIF, but we are going to talk about those in the next session. ADPS2 to ADPS0 are settings for the prescaler, which is 2 to the power of the value in ADPS. Unfortunately, the 13 clock cycles mentioned earlier that the ADC needs to sample an analog value is not in the same clock domain as the rest of the ATmega, which runs at 16 MHz currently. The ADC needs a slower clock between 50 and 200 kHz to ensure the highest accuracy. Therefore, in the Arduino setting, the prescaler is always set to its maximum of 128 to achieve a clock rate of 16 MHz divided by 128 equal to 125 kHz. How many times will the ADC sample the analog value if you write a program that can do it as fast as possible? Again, I'll pause the lecture here so you can rewind to the previous slides. Do you remember the slide where I showed the timing diagram? Let me pull it up again for reference. Each sampling takes 14 clock cycles of the ADC clock, 13 for conversion and 1 to set ADSC equal to 1. If the ADC runs at 125 kHz, it means that 8,928 times the analog value can be sampled at maximum. But let's tune it a bit. I clocked the ADC at 200 kHz somehow, and by some magic I can even save that single clock cycle in which the ADSC bit is set. So now 200 kHz and 13 clock cycles in total. That means my sampling rate goes up to 15,384 samples per second. Almost an improvement by 70%. But is that the maximum? Let's have a look at the datasheet in which the specifications for the ADC are listed. We have the 10-bit resolution. Check. We have the 6 channels. Check. We have the voltage reference. Check. We have the temperature sensor and many more. And we have the sampling rate mentioned. However, there's a huge difference between our maximum of 15 kilosamples per second and the one shown here, 76.9 kilosamples per second. In the brackets behind that, it is stated up to 15 kilosamples per second at maximum resolution, which is precisely what we computed earlier. Therefore, the question is, how do we get such a high sampling rate? It turns out that the accuracy can be sacrificed for speed. So what is the maximum clock frequency, assuming that 13 clock cycles are required? Well, it is the sampling rate multiplied by 13 cycles per sample, which results in 1 MHz. So the maximum frequency is 1 MHz. And that brings us back to the ADLAR setting in the ADMUX register. Imagine you ask the ADC to sample an analog voltage level, give it some time, and it returns the 10-bit value after that time. Now you're in a hurry and you do not want to give the ADC that much time anymore. So the ADC is stressed and most probably will get the last 2 bits wrong. They are the tricky ones anyway, since they influence the measurement by just a little bit, as we have seen in the examples earlier. But maybe you do not need that measurement to be that accurate. Maybe you just want to know if the analog voltage is either 1, 2, 3, 4 or 5 volt, and that's it. So you stress the ADC and give it not enough time to sample the last 2 least significant bits. In ADLAR equal to 0, these bits are set now. We have here ADC 9 to ADC 8 and ADC 7 to ADC 2. And we are not interested in these 2 bits. To get the value, I have to read out ADCL and shift ADC 7 to ADC 2 by 2 bits to the right. And then I read ADCH and move these 2 bits to the front. And then I can compute ADCH or ADCL. That is quite a bit of work for something that nobody is interested in. However, if I set ADLAR to 1, then I just need to read ADCH and can forget about anything that is in ADCL. I do not need to shift, there is no casting, and there are no multiple reads required from the registers. Convenient, isn't it? Therefore, if the software developer decides to run the ADC at frequencies larger than 200 kHz, it is very convenient to set ADLAR to 1 to discard the 2 least significant bits automatically. And the last 2 bits, ADIF, is the ADC Interrupt Flag. Therefore, conveniently, a conversion can be started and other parts of the program can be executed while the conversion is in progress. Once the value is ready, the CPU is informed about that event and an interrupt subroutine handling the reading is executed. That is different to the analog read command provided by the Arduino library, which blocks until the value is available. To use ADIF as an interrupt, also activate ADIE. Otherwise, ADIF needs to be polled constantly. And the other interesting bit is ADATE, which is an ADC auto trigger enable. There is the option to automatically sample the analog value not only by setting ADSC in software, but by selecting other sources. Okay, so this is the last configuration register with only 2 possible settings, ACME and several bits for ADTS. ACME stands for Analog Comparator Multiplex Enable. The ATmega is equipped with an analog comparator, which, as the name suggests, compares analog values. If the analog converter is not used, then the ADC pins can be used by the analog comparator instead. This ACME bit configures this setting. But at the moment, more interesting for us are the ADTS bits, which determine what else can trigger a conversion. First of all, there is the so-called free running mode, which we will handle in a bit. Then there is the comparator, which I just mentioned in the previous slide. But also external interrupt requests can be used. That can be, for instance, a trigger through a button press or a sensor sending a pulse through the int0 pin, which is port D2. But there are more. We can trigger the conversion based on a timer overflow or compare match, which is useful to sample at fixed time intervals. How does this work? As we know, the conversion logic can be started with the ADSC bit. So if that bit is set, the logic is clocked with a clock determined by the prescaler. But we have other sources as well, combined with the ADSC signal, shown by this OR gate. These other auto-triggering sources can be activated by the ADATE bit, which is one of the inputs to this AND gate. Now we can start the conversion by setting ADATE to 1 and the other input of the AND gate to 1, or by just setting ADSC to 1. The other inputs to that AND gate come from the sources. ADTS selects one of these sources. It goes then through an edge detector, which generates a pulse. So let's say ADIF toggles high. That means this line goes high, this line goes high, and this line goes high. ADATE is set to 1. That means this one goes up and this one goes up, despite the fact that ADSC is 0. This change will start a new conversion. Let's have a look at the timing diagram that we had earlier. This is a single conversion by just setting ADSC. In this case, ADATE is 0. As you can see, ADIF goes high if the conversion completed. And we talked about ADIF earlier. It can be used to trigger an interrupt subroutine to read out the converted value. It is cleared by executing the ISR or by writing a 1 to it. Then we have to trigger the next conversion by setting ADSC to 1 again, since as soon as the conversion completed, it becomes 0, as shown here. In the auto-triggered setting, the ADSC bit is simply replaced by the auto-triggering source, which might be the external interrupt or a timer compare match. Basically, it is the same as the ADSC with the difference that ADATE is set. There is one interesting mode though, and that is the free running mode. What if, as auto-triggering source, I select the ADIF bit? That ADIF bit is set once the conversion completed, but now it is also used as a triggering source. That means that as soon as one conversion ended, immediately the next one starts. And that is what we used when we calculated the maximum sample rate at the highest accuracy of around 15 kilosamples per second. Hence, for the free running mode, ADIF is selected and ADATE is set. Now we have to start the very first conversion by setting ADSC once. Once that is set, the ADC starts continuously converting the analog values. To stop it, set ADATE to 0 or select another source. In software, it will look like this. In this example, the ADIF bit is polled. As soon as ADIF goes up, it triggers the next conversion. We have to reset and clear manually the ADIF bit since only edges trigger the conversion. If ADIF is not reset by software, as in this example, or by an ISR, the conversion stops since ADIF remains high. The ADIF bit is cleared like in this scenario, followed by the data being read from the data registers. Imagine that the data is then communicated through a slow communication interface. Hence, we will not return to this code section on time to read the next sampled data, but we might skip some readings. We have to consider that the next time this code segment is executed, not the most recent value is in the ADC buffers, but the one of the conversion that was just executed after the last reset of ADIF. As a side note, the ADMUX is double buffered. During the conversion, the software developer can select other channels even in free running mode. The new setting becomes only active when the next conversion starts, so it does not mess up your readings. Also note, and that error is easily done. We have to read 10 bits from ADCH and ADCL. Therefore, the ADCH value needs to be cast to a 16-bit integer first before shifting the high byte by 8 bits. Otherwise, you shift out the 8 bits of the 8-bit unsigned integer of ADCH, which results in the value that is stored in ADCL only, without bits 9 and 10. Okay, that is all about the ADC for the moment. In the next session, we briefly talk about one method to reduce the power consumption and the noise for the channels. There is one register left that is specific to the ADC pins. Usually, the pins read digital signals. However, it is different for the ADC pins, which in addition can also read analog signals. If a pin is used as an analog channel, it is advisable to turn the digital input portion off, which reduces power consumption and noise. Why is that so? Here is the figure that I showed earlier in the course. Each pin consists of some logic to set the direction of the pin, what the pin should put out, and if the developer likes to read from this pin. Usually, there is no issue with that, since the transitions are from logic 0 to logic 1 only, as shown on the right side. If you read the pin digitally, this part converts the voltage either to logic 0 or 1. Every time a transition occurs, the read section consumes a bit of power to update its state. However, for an analog signal, the input looks very different. It is not in a logic 0 or logic 1 region all the time. It might flicker a lot depending on the analog value, or the voltage might linger in that undetermined section here. The problem is that the reading pin section might update itself with a high frequency, even if the voltage just changes a little bit. Every update consumes power and introduces a bit of noise on the pin line. Imagine that the noise caused by the update is just enough to cause another update. That means especially this flip-flop here changes its state even faster than clock I/O. To prevent this, the ADC pins have a special register called DIDR, or Digital Input Disable Register, with which the digital read section for each pin can be deactivated individually. The waveform on the right could be of a pin that is connected to an antenna, or might even be not connected to anything at all. In any case, it looks quite random. And we discussed randomness earlier when we talked about secure software programming and the seed for random number generators. In the same lecture, I showed the lava lamp wall by Cloudflare used in the video feed to generate numbers randomly. Most software developers do not have a lava lamp wall and take the time as some form of seed. Unfortunately, in ATmega, we do not have the capability to analyze a video feed nor a reliable time. After a reset, most likely the uptime is the same every time, leading to a seed which is always the same, and in turn to a sequence of random numbers which are, you guessed it, always the same. The ADC and the noise could be one way to alleviate the problem to some extent. Reading the unconnected and floating pins multiple times, or connecting them to some form of antenna to receive the electromagnetic radiation which is all around us, a random seed could be computed. This seed could show a higher level of randomness than many other options. It might not be secure cryptographically, but probably serves its purpose in many projects. That's all what I have for you today about the ADC. What did we do in this chapter? We talked about the ADC in length. It is able to convert an analog voltage level to a digital discrete value with a 10-bit resolution. Depending on the casing, there are 8 channels to sample from. In addition, the ADC can sample the Bandgap Reference, which can measure the state of the battery, for instance, and a temperature sensor, which is unfortunately not factory calibrated. To give the ADC enough time to convert the analog value, it should be clocked between 50 and 200 kHz. If accuracy is not a priority, that is, the least 2 significant bits are irrelevant, it can be clocked to up to 1 MHz. In the exercises attached to the end of this chapter, you will have to implement the oscilloscope that we used in the lecture about the DHT and the one-wire communication protocol. Make the sampling and transmission of data as fast as possible. In the next chapter, we will talk about the little brother of the ADC, the analog comparator, and the impact of the ACME bit that we had earlier in one of the ADC configuration registers. It cannot convert an analog value, but just returns if an analog value is higher or lower than a set threshold. So head over to the exercises to enjoy them. After that, I will see you again, and thanks for watching.